Sending an interstellar probe to another star is the ultimate test of human engineering. A vessel that must operate for centuries without human maintenance, enduring extreme cold, relentless radiation, and the slow decay of every material, all while remaining capable of communication and data collection. By the end of this video, you will understand exactly how such a machine could survive the void between stars. How do you design electronics that last longer than any civilization? And what happens to power systems that can never be refueled? The journey begins with a harsh environment that will test every component. What do you think is the biggest challenge for a probe that must outlive its creators? The space beyond our sun's influence is nothing like the void we imagine. Once a probe crosses the heliopause, the invisible boundary where the solar wind meets interstellar space, it enters a realm that is colder, emptier, and far more violent than anything we have encountered in our own solar system. The density of matter drops to just a few atoms per cubic centimeter, a vacuum so extreme that even the best vacuum chambers on Earth seem crowded by comparison. Temperatures plunge toward -270 degrees Celsius, just a few degrees above absolute zero. But cold is only part of the story. Without the sun's magnetic field to shield it, the probe will be pummeled by cosmic rays, high-energy particles that tear through materials and electronics. These particles are not just occasional stray protons. They come in steady, relentless waves, each one capable of disrupting a computer memory chip or degrading the structure of a solar panel over decades. A single cosmic ray striking a sensitive circuit can flip a bit, corrupt data, or even trigger a cascade failure. The interstellar medium is also filled with micrometeoroids, tiny grains of dust moving at tens of kilometers per second. Each impact may be microscopic, but over centuries, the cumulative damage erodes surfaces, pits lenses, and weakens structural joints. Designing a probe for this environment means every subsystem must be hardened against threats that simply do not exist in the inner solar system. A standard spacecraft computer would fail within years. A conventional power system would fade or freeze. The lessons learned from missions like Voyager are valuable, but those probes are merely dipping their toes into this ocean. To cross it, we need engineering that treats every particle, every photon, every degree of cold as a potential enemy. Understanding the environment is the first step toward building resilience. Only when we grasp the full brutality of interstellar space can we begin to ask the next question: how do you keep a probe alive when nothing can be repaired? The very first question that must be answered for any interstellar probe is not what it will study or where it will go. It is how it will keep the lights on. Power is the heartbeat of every system on board. Without it, the computer is a dead lump of silicon. The transmitter cannot whisper a single bit of data to home, and the instruments are just pieces of metal floating in the dark. And for a journey measured in centuries, the power source must last longer than any battery or fuel cell we rely on today. Solar panels, the workhorses of most inner solar system missions, become useless once a probe passes the orbit of Jupiter. Beyond the Kuiper belt, sunlight is so faint that even the largest solar array would produce less electricity than a wristwatch, so we have to turn to other options. The most proven technology for deep space power is the radioisotope thermoelectric generator, or RTG. These devices have flown on missions like Voyager, Cassini, and the Curiosity rover. They work by capturing the heat released from the natural decay of plutonium dioxide and converting that heat directly into electricity using thermocouples. No moving parts, no combustion, no refueling, just a steady, quiet trickle of power that lasts for decades. But there is a catch. The plutonium fuel decays at a fixed rate. After about 88 years, an RTG produces half the power it started with. Over a centuries-long mission, the output would drop so low that it could no longer operate the probe's essential systems. The Voyager probes, launched in 1977, are now running on less than half their original power, and engineers have had to shut down instruments one by one to keep the spacecraft alive. That is fine for missions that last 40 years, but for a probe that must function for 300 years or more, we need something better. That is where higher efficiency designs come into play. Instead of using simple solid-state thermocouples, engineers are exploring Stirling engines. A Stirling engine uses a piston driven by temperature differences to convert heat into mechanical energy, which then drives a generator. These systems can achieve nearly twice the efficiency of a traditional RTG, meaning they can extract more electricity from the same amount of plutonium. But moving parts introduce wear and vibration. On a mission that spans centuries, every moving component must be engineered to withstand long-term operation without lubrication or maintenance. Advanced thermoelectrics made from new materials like scutterudites or quantum well structures are another path. They offer higher conversion efficiencies without moving parts, but they still suffer from the same fundamental limit of decaying fuel. There is a more ambitious option on the table, a small fission reactor. Unlike an RTG, which uses passive decay, a fission reactor actively splits atoms to release energy. This yields far more power, potentially enough to run high-bandwidth communications, advanced ion thrusters, and a full suite of scientific instruments for the entire journey. A reactor can also be throttled, turned off, or even refueled if the probe carries spare fuel rods, but fission reactors come with serious trade-offs. They are heavy. The shielding required to protect the electronics and sensitive instruments from the reactor's own radiation adds significant mass, and the heat generated must be managed carefully because in the vacuum of space, the only way to shed heat is through radiators, which themselves add bulk and vulnerability. A reactor also introduces safety concerns for launch, though modern designs use fuel that is not radioactive until the reactor is activated in space. Still, the mass penalty and complexity make it a controversial choice. Whatever power source we choose, one thing is clear: every watt of electricity is precious. It must be conserved, stored, and routed with incredible efficiency. The probe's computer will have to sleep for years at a time, waking only to check its health or to listen for commands from Earth. The power system is the lifeline that keeps all other systems alive. Without it, the most brilliant instruments, the toughest shielding, the most resilient materials are all useless. So as we design this machine, we start not with the science payload or the communications array. We start with the power source because everything else depends on it. Building a power source that lasts centuries is only half the challenge. The real test lies in how that energy is stored and delivered moment by moment. Even a steady generator cannot supply power in perfect rhythm with every system demand. Instruments may need sudden bursts of electricity to run a sensor sweep, heat a critical component, or fire a tiny thruster for course correction. The transmitter, when it finally sends data back to Earth, draws many times the base load of the rest of the probe combined. If the power source itself is already weak from decades of decay, those peaks can overtax the entire electrical network. That is where energy storage becomes a lifeline. Batteries on an interstellar probe cannot be the same lithium-ion cells found in a laptop or an electric vehicle. Those cells lose capacity after a few years, especially when exposed to cold and radiation. Instead, engineers must turn to chemistries that offer extremely low self-discharge, meaning the battery loses almost no charge while sitting idle. A perfect candidate is a lithium thionyl chloride cell, which can hold its charge for 30 years or more, but even those degrade in the relentless cold of interstellar space. The answer might be to keep the batteries warm using a tiny fraction of the probe's power, or to use supercapacitors for short-term bursts. Supercapacitors can charge and discharge almost instantly, survive millions of cycles, and operate across a wide temperature range. But they hold far less energy than a battery, so they are best suited for handling power spikes, not for long-term storage. The power management electronics that sit between the source, the storage, and the loads must themselves be hardened against radiation. A single cosmic ray can cause a transistor to latch up, creating a short circuit that drains the battery or destroys the chip. Engineers design these circuits with triple redundancy, where 3 identical processors run the same calculations and vote on the result. If one fails, the other 2 override it. This approach, called triple modular redundancy, has been used on spacecraft for decades. For an interstellar probe, every power switching regulator, every voltage converter, every fuse must be designed to fail gracefully so that one damaged component does not take down the entire system. The storage system also needs physical redundancy. Instead of one large battery bank, the probe carries multiple smaller packs, each with its own charge controller and heaters. If one pack loses capacity, the others continue operating. The same applies to the supercapacitors. The entire power management unit must be able to self-diagnose and reconfigure itself, rerouting energy around failed sections without human intervention. This level of autonomy is essential because by the time a power failure is detected, the probe could be light years from Earth with no one to flip a switch. Now, all of these storage and management components generate heat when they operate, and that heat must be moved or dissipated to prevent damage. The power system cannot be considered in isolation. It interacts directly with the thermal management system, which uses radiators, heat pipes, and insulation to keep every part of the probe at the right temperature. As we move deeper into the design, we must see how these 2 systems, power and thermal, work together to create a self-regulating environment that can survive for centuries. The battery bank might need to be kept slightly above freezing, while the electronics must stay cool enough to avoid failure. Balancing those demands is one of the most delicate tasks in interstellar spacecraft engineering. Heat is both a friend and an enemy on an interstellar probe. Every electronic component, every circuit board, every scientific instrument needs a specific temperature range to function properly. Too cold and transistors stop switching, batteries freeze solid, and lubricants turn to glass. Too hot and solder joints crack, insulation melts, and sensitive detectors become useless. The vacuum of interstellar space offers no easy answers. There is no atmosphere to carry heat away, no ocean to absorb it, no planet to radiate it into. The only way to get rid of heat is by radiating infrared energy into the cold blackness of space. But that cold blackness is so cold that the probe itself might radiate heat away too fast. So the thermal control system has to walk a narrow tightrope, keeping the inside of the spacecraft warm enough while preventing the outside from freezing critical components or allowing waste heat from the power source to cook the delicate electronics. The first line of defense is multi-layer insulation, often called MLI. This is the shiny gold or silver foil that wraps around most spacecraft. It consists of many thin layers of reflective material separated by lightweight spacers. Each layer reflects thermal radiation back toward the spacecraft, and the vacuum between layers provides excellent insulation, but MLI is not perfect. Over centuries, micrometeoroid impacts can create tiny holes that allow heat to leak out. Radiation damage can darken the reflective surfaces, turning them from mirrors into absorbers. Engineers must design the insulation to remain effective even after decades of wear, using thicker layers or redundant blankets. Inside the probe, electric heaters powered by the main generator or batteries keep critical components at their operating temperature. These heaters are not simple glow plugs. They are smart, controlled by thermostats and software that monitor temperatures throughout the spacecraft. When a section gets too cold, a heater turns on. When it gets too warm, the heater shuts off. But every watt of heat from an electric heater comes from the precious power supply. So engineers also use passive methods like heat pipes. A heat pipe is a sealed tube containing a small amount of fluid, such as ammonia or water. At the hot end, the fluid evaporates, absorbing heat. The vapor travels to the cold end, where it condenses and releases heat. Then the liquid wicks back to the hot end. This cycle can move heat over distances without any moving parts. Heat pipes can carry waste heat from the power source or the computer away from sensitive areas and out to radiators that glow gently in the infrared. Those radiators themselves are a challenge. They must be large enough to shed waste heat, but they also need to avoid becoming so cold that they frost over with ice from outgassing or collect dust. Variable emissivity surfaces are a clever solution. These are materials that change how efficiently they radiate heat depending on their temperature or an applied electric voltage. When the probe is running hot, the surface becomes highly emissive, dumping heat quickly. When the probe is cold, the surface becomes reflective, keeping heat inside. These surfaces are made from advanced ceramics or thin film coatings that can be switched electronically, giving the spacecraft active control over its thermal balance without using moving shutters or louvers. The real difficulty is that everything degrades. The heaters draw less power as the source decays, so they cannot keep up as well over time. The heat pipes can slowly lose their working fluid through microscopic leaks. The MLI coatings darken, changing how much solar radiation they absorb from the occasional starlight or distant supernova. The variable emissivity surfaces can suffer from radiation damage that reduces their switching range. Engineers must model these aging effects and build in enough margin so that even after 300 years, the probe can still maintain a stable temperature inside its core. That core, where the computer and the most sensitive instruments live, must be kept in a narrow band around 20 degrees Celsius, plus or minus a few degrees. If the temperature drifts too far, the electronics can fail and the mission is over. So thermal control is not a one-time design. It is a balancing act that must self-correct over centuries, adjusting heater duty cycles, radiator orientation, and insulation effectiveness as the probe ages and the environment changes. And this careful balance leads directly to the next challenge: protecting the probe from the constant rain of energetic particles and micrometeoroids that threatens to punch through those very insulation blankets and disrupt every system inside. Shielding is the final barrier that keeps the hostile universe outside from turning the probe into a silent, drifting wreck. Every star in the galaxy is a natural particle accelerator, and interstellar space is filled with the debris it fires. The probe must survive two distinct kinds of radiation assault. The first is the steady, unending rain of galactic cosmic rays. These are particles, mostly protons and atomic nuclei, blasted to near light speed by supernova explosions and the hearts of distant galaxies. They are so energetic that they punch through solid metal, passing through hull walls and circuit boards as if they were fog. The second threat comes from the sun itself. As long as the probe remains inside the heliosphere, even far beyond Pluto, occasional solar flares can unleash bursts of high-energy protons. These events are less frequent than cosmic rays but far more intense, capable of overwhelming a spacecraft's electronics in a single surge. The challenge is that each type of radiation has a different energy and requires a different strategy. Galactic cosmic rays are relentless and almost impossible to stop completely. Solar particles are lower in energy but arrive in dense clouds that can short-circuit sensitive components and degrade instruments over time. To protect the brain of the probe, engineers must surround it with materials that absorb or scatter these particles. The most effective passive shields are rich in hydrogen, because hydrogen nuclei are about the same size as protons and are very good at absorbing their energy. Water is excellent, but water freezes and requires heavy containment. Polyethylene, the same plastic used in grocery bags, is much lighter and works almost as well. A jacket of polyethylene several centimeters thick can reduce the cosmic ray dose by a significant fraction, though not entirely. For added protection, the probe might carry its water supply for thermal management or propulsion in a layer that doubles as a radiation shield. But passive shielding adds mass, and every kilogram of plastic or water is a kilogram that cannot be used for instruments or thrust. So researchers are exploring active shielding. Instead of blocking particles, a magnetic field can deflect them, much like Earth's magnetic field protects us from the solar wind. A strong electromagnet wrapped around the probe's critical core would generate a bubble that sweeps charged particles aside. The power required for such a field is substantial, but with a high-output fission reactor it becomes feasible. The field could be tuned to handle the most common particle energies, while passive shielding absorbs the few that get through. The electronics themselves must also be hardened. Processors and memory chips made from silicon on insulator materials are less sensitive to radiation than standard chips. Error-correcting codes automatically fix corrupted data. Critical systems are triplicated so that a single bit flip does not bring down the whole computer. And the most vulnerable instruments, like optical sensors or spectrometers, can be stored in shielded vaults that open only when they need to observe. The goal is to ensure that after centuries of bombardment, the probe's core remains functional and its data remains accurate. If the radiation protection fails, the spacecraft becomes a drifting ghost, unable to think or communicate. But radiation is only part of the environmental assault. The same space that fills with particles also contains tiny grains of matter moving at bullet speeds. After crossing the heliopause, the probe will encounter interstellar dust, and those microscopic impacts pose a different kind of threat. A single grain of dust, smaller than a grain of sand, can destroy a critical component when it strikes at tens of kilometers per second. At those speeds, kinetic energy scales with the square of velocity, so a micrometeoroid weighing just a few micrograms hits with the force of a rifle bullet. The space between stars may seem empty, but it contains perhaps 100 such grains per cubic kilometer. Over a journey spanning centuries and crossing trillions of kilometers, the probe will face thousands of impacts, each one a micro-explosion that chips away at its skin, its instruments, and its ability to function. The classic solution for protecting spacecraft from micrometeoroids is called a Whipple bumper, named after the astronomer who first proposed it. It is deceptively simple. Instead of a single thick wall, you place a thin outer sheet a short distance in front of the actual pressure vessel or critical component. When a fast-moving particle hits that thin sheet, both the sheet and the particle are instantly vaporized into a hot cloud of plasma and debris. That cloud then spreads out as it crosses the gap, so by the time it reaches the inner wall, the energy is distributed over a much larger area. The inner wall, which can be much thicker, absorbs the remaining impact without being punctured. This same principle applies to an interstellar probe. The outer layers of the spacecraft, including parts of the thermal blankets and even the structural skin, act as sacrificial bumpers. They are designed to be destroyed in a controlled way, sacrificing themselves to protect the core. But a probe that must survive for centuries cannot rely on a single bumper layer. Over time, enough impacts can erode or perforate even the sturdiest outer sheet. So engineers design multiple layers like an onion shell. The outermost layer is a thin sheet of aluminum or Kevlar fabric that breaks up incoming particles into a spray. Behind it, a gap of perhaps a few centimeters, then a second layer that catches the spray. A third layer behind that catches anything that penetrates further. This layered approach means that even if the first two sheets are eventually riddled with holes, the third remains intact and the probe still functions. Some concepts use foam or honeycomb cores in between the layers to absorb energy and to stop any fragments that might ricochet. The entire outer shell becomes a sacrificial zone that slowly erodes over centuries, but the inner pressure vessel and electronics remain untouched. Certain vulnerable parts need extra care. The large antenna dish, for example, is a broad, thin surface that must maintain its precise shape to send data home. A single impact in the wrong place could create a hole or a dent that distorts the radio signal. Engineers might design the antenna with a self-healing mesh of conductive fibers. If a micrometeoroid cuts a few strands, adjacent fibers can bridge the gap, or a small electrical current can weld broken ends together. The same idea applies to thermal blankets. A puncture in the multi-layer insulation lets heat leak out, but a self-sealing patch made from a material that expands when exposed to vacuum could close the hole automatically. For the optical instruments like telescopes or spectrometers, the lenses or mirrors are particularly sensitive. A scratch from a micrometeoroid can scatter light and ruin measurements. So these instruments might be stored behind a transparent shield that is itself replaceable or covered with a thin protective film that can be peeled off after damage accumulates. Alternatively, the entire instrument could be housed in a rotating turret that presents a fresh, undamaged surface each time it operates. No single defense is enough. The combination of sacrificial bumpers, multiple spaced layers, self-healing materials, and careful placement of vulnerable components creates a multi-layered defensive system. Each layer is designed to degrade gracefully, absorbing the punishment of the interstellar medium one grain at a time, while the core of the probe remains unbroken. But all these protective shells need something to hold them together. The frame of the probe, the skeleton that supports every layer, every instrument, every thermal blanket, must be built from materials that do not weaken over centuries of vibration, radiation, and micro-impact erosion. The materials themselves must resist fatigue, corrosion from atomic oxygen or outgassing, and the slow creep of atomic displacement caused by radiation. The structural challenge is just as demanding as the shielding challenge, because without a strong, enduring skeleton, all the protection in the world cannot keep the probe in one piece. The skeleton of an interstellar probe must hold its shape for 300 years without cracking, bending, or becoming brittle. That demand eliminates most materials humans have ever built with. Ordinary aluminum alloys, for example, suffer from metal fatigue under repeated thermal cycling. As the probe rotates or as internal heaters cycle on and off, the frame expands and contracts. Over centuries, those tiny movements create micro-cracks that slowly grow until a critical joint fails. Steel is stronger, but it is heavy, and its density adds mass that must be carried across trillions of kilometers. Worse, steel can become embrittled by neutron radiation if the probe carries a fission reactor, turning a once tough metal into something that snaps like chalk. So engineers look to a new class of space-age alloys and composites. Titanium alloys offer a good balance of strength, low density, and resistance to fatigue. But titanium is difficult to machine and weld, and its thermal expansion coefficient, the amount it grows when heated, is not perfectly matched to other materials on the probe. That mismatch can create stress at joints where different metals meet. A better option might be a metal matrix composite, such as aluminum reinforced with silicon carbide fibers. These materials combine the light weight of aluminum with the stiffness and stability of ceramic fibers. They barely expand when heated and resist creep, the slow, permanent deformation that occurs under constant load over decades. Even more promising are carbon fiber reinforced polymers, the same materials used in high-end bicycles and aircraft. They are incredibly strong, almost completely immune to fatigue, and have near-zero thermal expansion. But polymers degrade under ultraviolet light and high-energy radiation. Over centuries in interstellar space, the resin that holds the carbon fibers together can become brittle and crack. The solution is to use a ceramic matrix instead of a polymer matrix. Carbon fibers embedded in a silicon carbide ceramic can withstand extreme temperatures, radiation, and micrometeoroid impacts while remaining lightweight. This type of composite is already used in the nose cones of hypersonic vehicles and the leading edges of re-entry capsules. For an interstellar probe, it could form the main structural truss, a rigid skeleton that holds all the subsystems together without sagging or twisting. Every joint, every fastener, every glue line must also be chosen with care. Regular epoxies outgas in vacuum, releasing molecules that can fog lenses or coat sensitive surfaces. So adhesives must be space-grade, specially formulated to have near-zero outgassing. Bolts and rivets must be made from materials that do not gall or cold weld, a phenomenon where two metals in vacuum fuse together under pressure. Engineers often use titanium fasteners with molybdenum disulfide dry lubricant to prevent this. Even the choice of welding technique matters. Friction stir welding, which joins metals without melting them, leaves fewer weak points than traditional fusion welding. One area of active research could revolutionize material longevity. Scientists are developing self-healing polymers that contain microcapsules filled with a healing agent. When a crack forms, the capsules break open and the healing agent flows into the gap, then hardens to repair the damage. On Earth, these materials can restore most of the original strength after a crack. In deep space, a self-healing structural panel could recover from micrometeoroid impacts or radiation-induced microcracks, extending the life of the frame far beyond what passive materials allow. Carbon nanotubes, rolled sheets of graphene atoms, offer another frontier. A structural cable made from nanotubes would be hundreds of times stronger than steel at a fraction of the weight. It would also conduct heat and electricity, resist radiation, and never fatigue. The challenge is manufacturing them in the long, continuous lengths needed for a spacecraft frame. Researchers have now produced kilometer-long nanotube ribbons, but the technology is not yet ready for a multi-century mission. Still, a future interstellar probe might rely on a skeleton woven from nanotube fibers, a structure so resilient that it could outlast the stars themselves. Every decision about materials affects the final reliability of the entire spacecraft. A frame that deforms by a fraction of a millimeter over a century can misalign a sensitive telescope or throw an antenna slightly off focus. A joint that weakens can allow vibration to grow and shake delicate electronics loose. The materials must work in harmony with the thermal control system, the power system, and the radiation shielding, because the structure is not just a skeleton. It is the stage on which every other subsystem performs, and if that stage warps, the entire mission fails. With the frame built to endure, the next layer of protection must fill the gaps. The probe needs a way to seal its interior from the vacuum, not just with solid walls, but with the equally critical ability to manage the internal atmosphere and pressure that keeps electronics and instruments alive. The most fragile part of any interstellar probe is its brain. The processors, memory chips, and sensors that give the spacecraft awareness and intelligence are also the most vulnerable to the relentless violence of deep space. A single cosmic ray can flip a bit in a memory cell, turning a 0 into a 1, corrupting a critical instruction, or scrambling a navigation command. Over centuries, the cumulative damage from radiation, the total ionizing dose, gradually breaks down the silicon lattice itself. Transistors become leaky, thresholds shift, and eventually the chip stops functioning. So the electronics must be built from the ground up to survive an environment that would destroy any off-the-shelf computer within years. The first line of defense is the manufacturing process itself. Radiation-hardened chips, often called rad-hard, are fabricated on special substrates like silicon on insulator. This design reduces the volume of silicon that can be ionized by a particle strike, making the transistor less sensitive. These chips are also built with larger feature sizes, older but more robust geometries that are less susceptible to single-event upsets. The trade-off is performance. A rad-hard processor today runs at a fraction of the speed of a modern phone chip, but it can withstand doses that would kill ordinary electronics in hours. But even the hardest chip is not immune, so the probe relies on error-correcting codes woven into every memory block. When data is written, extra bits are calculated and stored alongside it. When the data is read, those extra bits allow the system to detect and correct a certain number of flipped bits. This is the same technology used in your computer's RAM, but taken to a much higher level of protection. The codes can fix multiple errors per word, and the memory controller constantly scrubs through the entire memory, checking and repairing any corrupted cells before the errors accumulate. For the highest reliability, the most critical functions like the flight computer and the command decoder are triplicated. 3 identical processors run the same code, and a voting circuit compares their outputs. If one processor produces a different result, the other 2 override it. This triple modular redundancy ensures that even if a processor suffers a permanent failure, the system continues operating as if nothing happened. The failed unit can be reset or powered down, and the probe carries on with 2 processors until one of them can be repaired or replaced, though replacement is impossible on an interstellar mission. The memory that holds the probe's operating system and scientific data must retain information for centuries without power. That means no volatile RAM. Instead, engineers turn to non-volatile storage technologies like magnetoresistive RAM, or MRAM, which stores data in magnetic states that are not disturbed by radiation. Another option is phase change memory, which uses a material that switches between crystalline and amorphous states to represent ones and zeros. Both technologies can withstand billions of read and write cycles and hold data for hundreds of years without refresh. The probe's entire software library and mission plan will be stored in this kind of memory, duplicated across multiple banks so that if one bank degrades, another copy remains. Sensors, too, must be hardened. The imagers that will capture pictures of distant stars and planets use radiation-hardened CCDs or CMOS detectors that can operate in high-flux environments. Each sensor is calibrated with built-in reference sources that allow the system to measure and subtract the noise caused by accumulated radiation damage over time. The probe can even run self-tests, firing tiny heaters or internal light sources to check that every pixel responds correctly. If a pixel dies, the software can map around it. Despite all this hardening, electronics remain the most likely point of failure on the entire probe. A single undetected manufacturing flaw, a latent defect that only appears after decades of thermal cycling, can bring down the whole system. That is why every chip is tested, burned in, and screened with extreme rigor before it ever leaves the ground. And even then, the design must include graceful degradation. The probe does not need all its computing power to complete its mission. It can shut down non-essential processors, run on a single core, and prioritize only the most vital tasks. As failures accumulate, the spacecraft becomes simpler, but it stays alive. But hardware alone cannot make decisions. The real intelligence comes from the software that orchestrates every action, that decides when to sleep and when to wake, how to interpret sensor data, and how to heal itself when something goes wrong. And that software must be written with a level of robustness that far surpasses anything on Earth. hardware alone cannot think its way through a crisis. By the time a signal from Earth reaches an interstellar probe, the spacecraft could have drifted past a new discovery or stumbled into a dangerous situation hours, days, or even years earlier. Light itself is the limiting factor. Even at its fastest, a radio message traveling at the speed of light takes years to cross the distance to the nearest stars. Real-time control is impossible. The probe must be its own captain, its own engineer, and its own scientist, all rolled into a silicon brain that never sleeps and never gets distracted. That is where artificial intelligence becomes not just useful but essential. The onboard computer must constantly monitor every system, checking voltages, temperatures, radiation levels, and the health of each component. When a sensor reading drifts outside the safe range, the AI must diagnose the problem within milliseconds. Is it a true failure or just a glitch caused by a cosmic ray? If it is a real issue, the AI must decide how to reconfigure the spacecraft. It might reroute power from a non-essential heater to a failing thruster, or shut down a damaged instrument to protect the rest of the system. This kind of decision-making requires a deep understanding of the probe's own architecture, a kind of self-knowledge that must be programmed into its software before launch. But the AI does more than keep the probe alive. It also makes scientific choices. At interstellar distances, the probe will fly past objects and phenomena that no human has ever seen. A sudden spike in magnetic field readings, a faint glimmer from an unknown source, a change in particle density. The computer must decide in real time which observations are worth the precious power and data storage. It cannot beam every raw measurement back to Earth. The bandwidth is far too narrow, so the AI ranks each finding by its potential importance, compresses the highest priority data, and discards the rest. It learns from experience. Early in the mission, it might log every particle impact to calibrate its sensors. Later, it might notice a pattern in the data and adjust its filters to focus on rare anomalies instead of routine events. This kind of adaptive intelligence allows the probe to optimize its scientific return even as its own systems age and degrade, but software errors are inevitable. A bit flip can corrupt a critical instruction. A memory leak can slowly consume available storage. The AI must be able to repair its own code. It keeps a pristine copy of its operating system and all key algorithms in write-once memory, a read-only archive that cannot be altered by radiation. When it detects a software error, it reboots from that golden copy, then reloads the latest validated configuration. If the error persists, it can isolate the corrupted module and fall back to a simpler functional version. The computer also manages the probe's power budget with ruthless efficiency. It knows exactly how many watts are available from the generator, how much is stored in the batteries, and how much each subsystem consumes. It schedules activities like firing a thruster or taking an image during periods when the power supply has spare capacity. It can even decide to enter a deep sleep state for years at a time, waking only to check for critical changes or to listen for a command from Earth. Every cycle of every clock, every allocation of every milliampere is planned and executed by the AI, and it does all of this without any human oversight. By the time a problem becomes visible from Earth, the probe may have already solved it or, in the worst case, already failed. The margin for error is zero. The AI must be flawless, not in the sense of never making mistakes, but in the sense of always recovering from them. This level of autonomy pushes current technology to its limits. But it also opens the door to a new kind of exploration. The probe becomes a partner in discovery, not just a remote tool. It can adapt to the unexpected, follow its curiosity, and send home the most valuable pieces of a story that spans centuries. Yet even the most brilliant AI is useless if it cannot deliver its findings. And that brings us to the most daunting challenge of all. sending a whisper of data back across the light years of emptiness that separate the probe from its creators. The faintest whisper of a signal must travel for years before it reaches home, and by the time it arrives, it is so weak that it barely rises above the random noise of the universe. This is the cruel reality of interstellar communication. The inverse square law dictates that as a radio wave spreads outward, its power drops off with the square of the distance. Double the distance and the signal is 4 times weaker. Triple it and it is 9 times weaker. At the distance of the nearest star, a signal that was 1,000,000 watts when it left the probe would arrive at Earth with less power than a single photon per second. That is not a conversation, that is a vanishing whisper in a cosmic hurricane. To have any hope of being heard, the probe must focus its transmission into an incredibly narrow beam. Instead of broadcasting in all directions like a lighthouse, it must shine a laser with the precision of a surgeon pointing a scalpel from thousands of kilometers away. The leading concept is a laser communication system paired with a large telescope on the probe. The laser itself can be relatively modest in power, perhaps a few hundred watts, but because the beam is so tightly collimated, the energy remains concentrated over vast distances. The telescope, perhaps a meter or more in diameter, acts as the final lens, squeezing the beam down to a divergence angle measured in millionths of a degree. At that level of focus, the spot of light arriving at Earth is still many times the diameter of our planet, but it is far brighter than a diffuse radio wave. Yet focusing the beam is only half the battle. The probe and Earth are both moving. The probe is hurtling through interstellar space at tens of kilometers per second, and Earth is racing around the Sun at nearly 30 kilometers per second. The direction the probe points its laser today will not be the direction Earth will be in when the light arrives years later. The navigation and pointing system must calculate a precise lead angle, a kind of cosmic aiming correction that accounts for both motions. This calculation must be accurate to within a few thousandths of a degree, maintained continuously for centuries. Any drift in the probe's attitude, any tiny thermal expansion of the telescope structure, any jitter from a micrometeoroid impact, and the beam will miss Earth entirely, and the message will be lost in the void. On the receiving end, Earth must also be ready. The signal is so faint that even the largest radio telescopes, dishes hundreds of meters across, would struggle to detect it. Instead, the receiving stations will likely be arrays of optical telescopes, each equipped with superconducting detectors cooled to near absolute zero. Cooling reduces the thermal noise inside the detectors so that a single photon becomes detectable. These receivers will be spread across the globe, perhaps on mountaintops or in deserts, so that at least one can be pointed toward the probe's predicted position at any given time. The data rate will be painfully slow, a few bits per second at best, but every bit is a triumph of engineering. A single image of a distant star system could take weeks to transmit. The probe's own antenna pointing system must remain in perfect alignment for centuries. That means the actuators that steer the telescope, the gyroscopes that sense rotation, and the star trackers that identify reference points must all function without degradation. The probe carries multiple redundant units, but even so, the system must be able to detect its own misalignment and correct it using onboard algorithms. If a star tracker loses calibration, the probe can use the Sun or even bright planets as backup references. If the laser itself drifts, the probe can dither the beam in a tiny pattern and analyze the returned signal, if any, to fine-tune the aim. But all this precision depends on one thing: knowing exactly where the probe is. The navigation system, the invisible thread that ties the probe's position to Earth's, must be accurate to within a few hundred kilometers over a journey of trillions. Without that knowledge, every pointing calculation is guesswork, and every transmitted signal is wasted. So how does a spacecraft that cannot see its own home chart its path through the darkness? The answer lies in the stars themselves and the way they appear to shift as the probe moves across the galaxy. The stars themselves become the probe's map. As the spacecraft drifts farther from the Sun, the familiar landmarks that ground-based tracking relies on grow impossibly faint. Radio signals that would once have pinpointed its position with kilometer accuracy become lost in the static of the galaxy. Earth's own transmissions weaken to a whisper, and the probe can no longer depend on being told where it is. It must navigate by the light of distant suns and the rhythmic pulses of dead ones. That is where pulsar navigation enters the picture. Pulsars are rapidly spinning neutron stars that beam out regular flashes of radiation like cosmic lighthouses. Each pulsar has its own unique rhythm, a signature pattern that remains stable for millions of years. By measuring the arrival times of pulses from multiple pulsars, the probe can triangulate its position in three-dimensional space with remarkable accuracy. The technique is similar to how GPS works on Earth, except the satellites are entire stars. The onboard computer compares the observed pulse timings against a stored catalog, then calculates a fix. Because pulsars are scattered across the sky, the probe can always find at least a few in view, no matter how far it travels. Yet pulsar navigation alone is not enough. It tells the probe where it is, but not which way it is facing. For that, the spacecraft relies on star trackers, cameras that take images of familiar constellations and compare them to an onboard star map. By identifying the positions of bright stars in the field of view, the computer can determine the probe's orientation, its attitude, down to a tiny fraction of a degree. These star trackers are small, rugged, and consume very little power, but they must be kept clean and free of dust or micrometeoroid pits, and their lenses must stay aligned over centuries. Gyroscopes fill in the gaps between star tracker updates. Inside the probe, spinning wheels or laser rings sense every rotation of the spacecraft. They measure how fast the probe is turning and in which direction, allowing the computer to know its orientation at every instant, even when no star is in sight. But gyroscopes are not perfect. Over months and years, tiny imperfections in their bearings or laser cavities cause them to drift, slowly accumulating errors. A gyro that is off by 1/1000th of a degree today might be off by a full degree after a decade. That drift would be catastrophic when pointing a laser antenna at Earth or firing a thruster for a course correction, because even a tiny misalignment sends the beam or the thrust vector far off target. So the probe must periodically recalibrate its gyroscopes using the star trackers. Whenever the spacecraft is idle, it slews its cameras toward a known star, takes a precise reading, and adjusts the gyro offsets. This recalibration becomes a routine maintenance task, scheduled automatically by the onboard computer. Over the centuries, thousands of such calibrations keep the orientation system healthy. The precision required is staggering. To fire a thruster that changes the probe's trajectory by just a few meters per second, the computer must know the probe's orientation to within a few millionths of a degree. To point its laser back at Earth, the same level of accuracy is needed, and it must be maintained for the hours or days it takes to transmit a single image. Any error in orientation means the beam misses Earth entirely and the data is lost. That is why navigation and attitude control are not separate systems. They are two halves of a single feedback loop. The pulsar fixes tell the probe where it is. The star trackers and gyroscopes tell it which way it is pointed. And together, they enable the spacecraft to execute maneuvers with a precision that rivals the finest laboratory instruments on Earth. This loop must run continuously, silently, for 3 centuries. If a star tracker fails, a backup takes over. If a gyro drifts too far, the computer switches to a redundant unit. The software constantly checks for consistency, comparing the pulsar navigation solution against the inertial readings. If they disagree, the probe enters a diagnostic mode, halting all non-essential activities until the discrepancy is resolved. The stakes are absolute. A navigation error that goes uncorrected for even a few months could send the probe hurtling past its target star with no way to return. And so the guidance system, the hidden brain of the probe, must be as resilient as the hull that shields it from the void. It must keep its bearings not just for years, but for generations, so that when the probe finally arrives at its destination, it knows exactly where it is and exactly where to look. Knowing where you are means nothing if you cannot keep yourself pointed in the right direction. The probe must hold its gaze steady for centuries, aiming its laser antenna at an Earth that is itself moving and rotating, while also adjusting its own trajectory by tiny amounts to stay on course. Doing all this without wasting a single drop of propellant is one of the hardest problems in interstellar engineering. The workhorses of attitude control are reaction wheels. These are massive, precisely balanced flywheels, spinning at thousands of revolutions per minute inside the spacecraft. By speeding up or slowing down a wheel, the probe can rotate itself in the opposite direction, thanks to the conservation of angular momentum. No thrusters, no fuel, no exhaust, just pure physics. To point its telescope at a star, the computer commands one wheel to spin faster, and the entire spacecraft turns gracefully. To stop the rotation, it commands another wheel to counter the motion. A set of 3 or 4 wheels mounted on different axes gives the probe full control over its orientation. The beauty of reaction wheels is that they use only electricity, and electricity can be generated continuously from the power source. Over a century of operation, a properly designed wheel might spin for billions of revolutions without consuming any propellant. That is the ideal, but reality complicates the picture. The bearings that support the spinning mass are subject to friction, micro-vibrations, and slow material degradation. Even in the vacuum of space, lubricants can evaporate or become contaminated over decades. Microscopic wear particles can roughen the bearing surfaces, creating vibration and eventually leading to seizure. Engineers have developed several solutions to this problem. Some reaction wheels use magnetic bearings that levitate the spinning rotor, eliminating physical contact and friction entirely. These bearings require active control and power, but they can last indefinitely because nothing touches. Others use a hybrid design, where magnetic bearings lift the load at high speeds and mechanical bearings are only used at low speeds or during start-up. Redundancy is critical. A typical probe carries 4 reaction wheels, one more than required for full 3-axis control. If one wheel fails, the others can reorient the spacecraft, though the maneuvers become slower and more constrained. Reaction wheels alone, however, cannot handle every need. Over time, external forces like sunlight pressure or tiny gravitational tugs from passing asteroids can slowly build up angular momentum in the wheels. If the wheels reach their maximum spin speed, they cannot absorb any more momentum, and the probe loses the ability to control its orientation. This is called momentum saturation. To fix it, the spacecraft must bleed off the excess momentum using thrusters or another device. On a long mission, that would mean carrying propellant, the very thing we are trying to avoid. That is where alternative methods become essential. One elegant solution uses the communication laser itself. When the probe transmits a laser beam back to Earth, the photons carry momentum. By shifting the direction of the beam very slightly, the probe can create a tiny torque that counteracts any build-up in the reaction wheels. This photon pressure is incredibly small, but over months and years it adds up. The system can make micro-adjustments to the laser pointing, and the resulting recoil spins the probe just enough to desaturate the wheels. No propellant consumed, no moving parts beyond the laser steering mirror. Another possibility is a solar sail. Even in interstellar space, there is a faint but constant pressure from sunlight. and even fainter pressure from the cosmic microwave background. A very large, very lightweight sail could generate a minuscule force over centuries, enough to make course corrections without fuel. The sail would have to be deployed after launch and kept taut, but it offers a zero propellant maneuvering capability. For tiny trajectory tweaks, like arriving at a star system at the right angle, that sail could be the difference between a flyby and a direct hit. Yet all these systems rely on one thing: timing. A reaction wheel that turns a fraction of a second too late can misalign the laser. A laser desaturation that lasts a millisecond too long can push the probe off course. The onboard clock must be the most accurate and stable ever flown. Without precise time, every orientation command is a gamble, and every navigation fix is uncertain. The probe cannot afford to be even a single microsecond off over the course of its long journey. Time itself becomes a physical component of the spacecraft, as real as any battery or circuit board. Every measurement the probe makes, every image it captures, every pulse of laser light it sends home depends on a shared understanding of when things happen. If the onboard clock drifts by even a fraction of a second over a century, the pulsar navigation solution becomes useless. The laser beam misses Earth by thousands of kilometers, and the scientific data loses its context. Without precise time, the probe is blind and deaf. So engineers embed an atomic clock at the heart of the system, a device that ticks not with a quartz crystal, but with the natural vibration of atoms. The most practical design for an interstellar mission is a chip-scale rubidium clock, small enough to fit in a matchbox, consuming only a few watts of power. It works by shining a laser through a tiny cell of rubidium gas and measuring how the atoms absorb the light at a specific frequency. That frequency never changes. It is locked to the fundamental properties of the atom, making it as stable as the laws of physics allow. In a laboratory, these clocks can lose or gain less than 1 second over millions of years. In space, the challenge is keeping that performance alive through radiation, temperature swings, and the slow aging of the laser and the gas cell. The clock must be kept in its own temperature-controlled chamber, insulated from the rest of the probe. Even a slight variation in heat can shift the laser wavelength, causing the clock to drift. Redundancy is essential. The probe carries 3 atomic clocks, each in its own shielded housing, running continuously. Their outputs are compared by the computer, which calculates a weighted average. If one clock begins to drift, the other 2 override it, and the faulty unit can be reset or powered down. But atomic clocks are not the only reference. The pulsars themselves offer a natural time signal that the probe can use as a backup. Every few years, the computer can perform a calibration, listening to the steady rhythm of a known pulsar and comparing its own internal clock against that cosmic metronome. Even if the atomic clocks degrade over centuries, the pulsar pulses provide an absolute check, keeping the spacecraft aligned with the universe's own heartbeat. This timing feeds directly into every other function. When the probe schedules a data transmission, it must know exactly when Earth will be in the right position to listen. When it captures an image, the precise timestamp tells scientists later exactly when the light left the target. The computer itself uses the clock to sequence its own internal operations, waking subsystems, running diagnostics, and sleeping again on a schedule that would be impossible to maintain without nanosecond accuracy. A single microsecond error can throw off an entire observation campaign. Over 300 years, the cumulative drift must be kept below a millisecond, a requirement that pushes atomic clock technology to its limits. The design of this timekeeping system is as critical as the design of the power source or the shielding, because without it, the probe cannot know where it is, when it is, or how to tell anyone else what it has found. But knowing exactly when and where you are is pointless if the instruments meant to explore the unknown have already gone silent. Every sensor on board, every magnetometer, dust analyzer, plasma detector, and camera must survive the same punishing environment as the rest of the probe, and they must do so while remaining sensitive enough to detect the faint whispers of the cosmos. The magnetometer is a deceptively simple device, just a set of coils that measure changes in magnetic fields. But over centuries, radiation can slowly degrade the insulation on its wires, creating tiny leakage currents that drown out the real signal. To counter that, engineers wind the coils with radiation-resistant enamel and encase them in a separate shielded housing far from the power source. The magnetometer also carries an in-flight calibration source, a small coil that generates a known magnetic pulse. Every few years, the probe fires this pulse and compares the reading to the expected value. If the sensitivity has drifted, the computer updates its calibration table, keeping the measurements accurate even after decades of exposure. Plasma detectors face an even harsher fate. They collect charged particles that stream past the spacecraft, but those same particles can damage the detector's front window, a thin foil that lets particles in while blocking light. Over time, micrometeoroid impacts can puncture that foil, letting unwanted light flood the sensor and ruin the measurement. The solution is to carry a roll of spare foil, like a film canister, that the probe can unroll to replace the damaged window. The deployment mechanism is rugged, using a simple spring-loaded spool that has been tested for thousands of cycles. And because the detector uses high voltage to accelerate the incoming particles, the electronics that generate that voltage must be potted in a radiation-hardening resin to prevent arcing across the vacuum. Dust analyzers are among the most sensitive instruments. They measure the mass, speed, and composition of tiny grains by letting them slam into a metal plate and vaporize. The resulting plasma is then analyzed by a mass spectrometer. The problem is that the impact plate itself erodes over time, especially when the probe passes through a region of higher dust density. To compensate, engineers make the plate thicker than needed and include a reference impactor, a tiny device that fires a known grain of material at the plate during calibration. By analyzing the signal from that artificial impact, the probe can adjust its measurements to account for the wear. The cameras are perhaps the most fragile. A single layer of frost on a lens or a scratch from a micrometeoroid can scatter light and ruin images. So each camera has a heated window made of sapphire, a crystal that is nearly as hard as diamond and resistant to radiation darkening. The window is kept a few degrees above the surrounding temperature to prevent ice from forming. Behind the window, a shutter mechanism opens only when the camera is actually taking a picture, protecting the sensor from stray light and particles the rest of the time. But even the sensor itself, a radiation-hardened charge-coupled device, will accumulate defects over the years. Hot pixels, bright spots that never turn off, appear as radiation damage mounts. The solve is to take regular dark frames, images with the shutter closed, that measure the pattern of hot pixels. The computer then subtracts that pattern from every future image, removing the noise and keeping the pictures clear. Every instrument is duplicated, sometimes triplicated, so that if one fails, another can take over. But even with redundancy, the probe cannot afford to lose a single capability. The dust analyzer might be the only one that detects organic molecules. The camera might be the only one that sees a planet's rings. So each instrument is designed to degrade gracefully, losing sensitivity slowly over time rather than failing outright. The calibration systems, the heaters, the redundant sensors, all work together so that after 300 years, the probe can still deliver a measurement that scientists on Earth can trust. And it is those measurements, those faint signals from the edge of the unknown, that will become the probe's legacy. The data it collects will reveal the composition of interstellar dust, the strength of magnetic fields between stars, the density of plasma in regions no human spacecraft has ever visited. Each reading will be a message from a place that has remained silent for billions of years, waiting for a machine brave enough to listen. All those readings become worthless if the memory holding them decays. The probe will gather a treasure of data over centuries, a stream of measurements from a place no human has ever reached. But that information must survive not years but generations, stored in a medium that can hold its contents without power for decades at a time, yet allow new discoveries to be written alongside the old. This is a paradox. The same radiation that threatens every circuit on the spacecraft also attacks every bit of stored data. A single cosmic ray can flip a 1 to a 0, and over centuries, those flips accumulate until the data becomes unrecognizable, a silent corruption that slowly erases the mission's purpose. The solution is a layered approach that combines tough hardware with intelligent software. For the primary storage, engineers turn to radiation-hardened flash memory, chips built on specialized manufacturing processes that resist the ionization effects of high-energy particles. These chips are slower than consumer flash and hold less data per square millimeter, but they can withstand doses that would destroy ordinary memory in hours. Yet even hardened flash is not immune. Over centuries, the insulating oxides that trap charge can leak, and the stored bits can drift like sand in a slow wind. So the probe also carries a backup system using magnetic core memory, a technology that dates back to the earliest days of computing. In core memory, each bit is stored as the magnetic orientation of a tiny ferrite ring, and that orientation is not affected by radiation or by the passage of time. Core memory is bulky and heavy compared to flash, but it is also practically indestructible. The most critical data, the probe's operating system, navigation tables, and the golden copy of its software, is stored in core memory banks that are triple redundant. Every vital bit exists in 3 separate cores. If one core suffers a failure, the other 2 override it. Emerging technologies offer even more promise. One of the most intriguing is DNA storage. Synthetic DNA molecules can encode enormous amounts of information in an incredibly small volume, at densities that dwarf any electronic memory. A gram of DNA could store the entire collected works of human knowledge, and DNA is stable for tens of thousands of years if kept cold and dry. On an interstellar probe, a small reservoir of synthetic DNA could act as a backup archive for the most precious data. The readout mechanism is still complex, requiring a miniature laboratory that can sequence the DNA strands, but the long-term stability is unmatched. Whatever storage medium is used, the probe must constantly fight against bit rot. Every piece of data is stored with error-correcting codes, extra information spread across the bits that allows the computer to detect and fix a certain number of errors. But even those codes are vulnerable, so the computer runs a background process called scrubbing. It reads through every memory location, checks the error-correcting codes, and repairs any corrupted bits. It does this continuously, cycling through the entire storage over and over again, so that no single bit remains corrupted for longer than a few days. Scrubbing catches the errors that accumulate from recent cosmic ray strikes before they can compound into a permanent failure. Between the physical resilience of hardened flash and magnetic core memory, the massive capacity of DNA storage, and the constant vigilance of scrubbing, the probe's data remains intact. But even scrubbing cannot fix a direct hit on a critical memory cell. That is where the final layer of protection comes in. The most sensitive data is stored not just with error correction, but with spatial redundancy. The same information is stored in multiple physical locations across different memory chips and different core banks. If one location is struck by a high-energy particle that scrambles its contents beyond repair, the other copies remain untouched. The computer can detect the corruption, flag that location as bad, and copy the data from a surviving bank to a fresh location. This self-healing storage system means that even after centuries of bombardment, the probe's memory remains accurate. And it is this accurate memory that will one day be unpacked, bit by bit, into a signal aimed at a distant blue dot, carrying the first real account of what lies between the stars. Redundancy is not a luxury on this probe. It is the only guarantee of survival. Every critical subsystem, from the flight computer to the power regulator to the attitude control wheels, exists in at least 3 copies. The underlying philosophy is simple. If one unit fails, the second takes over, and if that one fails, the third waits in reserve. But redundancy alone is not enough. Without a way to choose which unit is correct, 3 copies can disagree, and the probe would be paralyzed by indecision. That is where voting logic enters the picture. In the flight computer, 3 identical processors run the same instructions at the same time. Their outputs are fed into a simple circuit that compares them. If 2 processors produce the same result and the third differs, the majority wins, and the outlier is flagged as faulty. The probe can then reset that processor or power it down entirely, isolating the failure before it can corrupt the rest of the system. This triple modular voting ensures that a single bad chip or a single corrupted bit never takes down the brain. The same logic extends to every sensor reading. 3 magnetometers measure the same field. If one reading drifts away from the others, the computer knows that instrument has degraded and excludes it from the navigation solution. But the real art lies in graceful degradation. The probe is not designed to run at full capacity forever. It is designed to lose components slowly, one by one, without ever losing its core mission. When a reaction wheel seizes after 200 years, the remaining 3 wheels reconfigure themselves to handle the load. The spacecraft may take longer to rotate, and pointing accuracy may drop by a tiny fraction, but the telescope still steers and the laser still locks onto Earth. The computer gradually shifts its operating mode, shutting down non-essential instruments and conserving power. The probe becomes simpler, leaner, but it stays alive. Isolation between redundant units is just as important as having spares. If all 3 processors share the same power bus, a short circuit in one can kill the others. So each redundant unit has its own dedicated power line, its own fuse, its own radiation shield, and its own communication channel to the rest of the spacecraft. A failure in one compartment does not spread to its neighbors. The wiring harnesses are routed in physically separate conduits so that a micrometeoroid impact that severs one set of cables leaves the backups untouched. This isolation applies at every level, from the structure to the software. The software that controls the primary computer is stored in a memory bank that is physically separate from the backups. Even a serious software fault that corrupts the main memory cannot reach the spare copies stored in the core memory vaults. This layered approach to redundancy does more than just keep the probe running. It gives the spacecraft the ability to repair itself. When a component fails, the computer detects the loss, isolates the faulty unit, and activates a spare. It does not need a human to diagnose the problem or flip a switch. The decision happens in milliseconds, automatically, without any intervention. Over decades, the probe will use up its reserves one by one, shedding parts like a tree shedding leaves. But the trunk remains and the mission continues. By the time the probe arrives at its destination, it may be running on its last reaction wheel, its last atomic clock, its last communication chain. But it will be running, and that is the entire point. Redundancy, graceful degradation, and isolation are not separate concepts. They are 3 parts of a single design principle. Build the probe to survive its own inevitable failures. Redundancy buys time, but only diagnosis turns that time into survival. The probe cannot simply wait for a component to fail and then blindly activate a spare. It must listen to itself constantly, monitoring every voltage, every current, every temperature reading, every vibration pattern across the entire spacecraft. This is not a background task that runs once a day. It is a continuous, system-level heartbeat that cycles thousands of times per second. The onboard computer compares every measurement against a stored baseline, a digital map of how the probe should behave when everything is healthy. When a reading drifts even slightly outside the allowed range, the computer flags that subsystem and begins a diagnostic routine. It runs a series of tests, sending known signals through the component and measuring the response. Is the power supply output sagging because the regulator is aging, or because a downstream short is drawing too much current? Is the reaction wheel vibrating more than usual because its bearing is wearing, or because a micrometeoroid impact has thrown off its balance? The computer must answer these questions with only the data it can gather in the moment, and it must answer quickly because a failing part can sometimes cascade into a larger failure if left unchecked. Once the diagnosis is made, the probe can reconfigure itself. It can switch to a backup unit, reroute power around a damaged circuit, or adjust its operating parameters to compensate for a degraded sensor. But not every failure can be fixed with software alone. Some components are so critical that the probe must carry physical spares. This is where the concept of a black box comes in, a heavily shielded vault deep inside the spacecraft that holds a carefully chosen set of replacement electronics. These are not random circuit boards. They are the most likely to fail parts, power regulators, memory banks, processor modules, and critical sensor front ends. Each spare is stored in its own compartment, protected by its own radiation shielding and thermal insulation, so that even if the primary systems near the black box are damaged, the spares remain pristine. When the computer determines that a primary component has failed beyond its ability to work around, it can electrically switch in a spare. No astronaut, no toolkit, no soldering iron required. The spare simply takes over the same data and power lines that the failed unit used. That switch happens in milliseconds, and the probe continues its mission with barely a hiccup. The idea of physically swapping a module using a robotic arm is far more tempting in theory than in practice. A simple gripper mechanism could slide out a failed unit from its slot and push a fresh one into place, but that mechanism itself adds mass, complexity, and another potential failure point. Every joint, every motor, every gear in that arm must be hardened against the same radiation and cold that threatens every other part. And the arm would need its own power, its own control electronics, its own soft landing system to prevent it from damaging the delicate components it is trying to replace. For a probe that must last centuries, the total mass penalty of such a system often outweighs the benefit. It is simpler and more reliable to carry multiple identical units already installed in parallel. Instead of swapping a failed power supply, the probe can just turn off the faulty one and let the remaining supply take over. That approach requires no moving parts, no robotic arm, no complex mechanical choreography. The mass that would have gone into the arm is instead used for an extra power supply board. The trade-off is always the same. Physical repair adds flexibility but also adds risk. Engineers must decide where the line falls for an interstellar probe. For the most critical systems, like the flight computer and the power management unit, the best strategy is high redundancy with electronic switching. For less critical but still important components, like certain science instruments, a robotic arm might be worth the mass if it means the difference between gathering data for 200 years versus 400 years. In the end, every gram of spare parts and every mechanism for using them must earn its place on the manifest. The probe cannot carry a full factory. It can only carry what was known to fail on previous missions, plus a margin for the unexpected. The black box becomes a strategic reserve, a silent insurance policy that may never be used but must be ready for the moment it is needed. All these hardware decisions, the spares, the diagnostic routines, the switching networks, are useless without a layer of software that ties them together. That software must know not only how to detect a failure, but how to decide which spare to activate, when to do it, and whether the repair is worth the power and the disruption to the mission. It is the final, invisible layer of self-preservation that turns a collection of parts into a machine capable of healing itself. Every switch, every sensor, every redundant circuit in that probe relies on a single line of code to know when to act. Hardware is the skeleton, but software is the nervous system, and a nervous system that cannot adapt is a nervous system that will eventually fail. The challenge is that no amount of pre-flight testing can simulate every scenario the probe will face over centuries. A cosmic ray might trigger a rare timing glitch that was never seen on Earth. A micrometeoroid impact might leave a thruster stuck slightly open, creating a slow rotation that the attitude control software was never programmed to handle. An unexpected pattern in the interstellar magnetic field could confuse the navigation algorithms, sending the probe into a search loop that slowly drains the batteries. The probe must be able to fix its own mind. That means it must have the ability to receive and apply software updates, even when the round-trip communication time stretches to years. The update mechanism itself is a work of careful engineering. The probe carries a small, hardened kernel of code, a minimal operating system that is stored in the radiation-proof core memory banks. This kernel is verified, meaning that every possible path through its logic has been mathematically proven to behave correctly under all conditions. It is the seed from which everything else grows. When a new update arrives from Earth, a trickle of bits traveling at the speed of light, the kernel is the only part of the software that is trusted to receive it. The kernel checks the update's cryptographic signature, verifies that no bits were corrupted during the long journey, and only then applies the patch to the rest of the system. This process allows the probe to rewrite its own instructions, to learn from its mistakes, and to adapt to conditions that no engineer on Earth could have predicted. The updates themselves are written with the same formal verification techniques used for the kernel. Every line of new code is proven correct before it is ever transmitted. There is no room for a bug that only appears after 100 years, because by then no one will be left who remembers the original design. The software is also redundant in its own way. The same critical functions are implemented in 2 or 3 different versions, each written by a different team using different algorithms. If one version produces a result that the others disagree with, the system votes and selects the majority answer. This diversity of implementation means that a subtle logical error in one version does not bring down the entire probe. Over time, the software evolves. Patches are applied, new behaviors are added, obsolete routines are retired to save memory. The probe becomes a living archive of human ingenuity, its code a slowly growing palimpsest written across the decades. And just like the hardware, the software is designed to degrade gracefully. If a memory chip containing a critical driver fails, the system can reload that driver from a backup copy stored in a different physical location. If an algorithmic error is detected, the probe can revert to an earlier, known good version of that routine. The machine learns to work around its own limitations. By the time the probe reaches its destination, its software may bear little resemblance to the code that first booted up in Earth orbit. It will have been patched, rewritten, optimized, and hardened by centuries of real-world operation. That durability is not an accident. It is the result of treating software with the same respect as hardware, designing it not just to work on launch day, but to survive decades of silence, to accept updates from a home that is slowly receding into the distance, and to carry the mission forward even when the engineers who wrote the original code are long gone. The mind of the probe must be as tough as its body, because in the end it is the mind that decides what the body does, and that mind must remain sharp, focused, and adaptable for the entire journey. All that preparation is meaningless without a single moment of perfection on launch day. The months and years of design, the careful selection of every material, the 1,000 hours of testing, all of it funnels into a few minutes of fire and vibration that will either send the probe on its way or shatter it into 1,000 pieces. The rocket itself must lift a payload that is heavier than any interplanetary probe ever built, because this machine carries not only its own weight but the weight of redundancy, shielding, spare parts, and a power source that will outlast its builders. The ascent through the atmosphere is a violent shuddering that rattles every joint, every solder point, every delicate instrument. The probe's structure must absorb and dampen that vibration without transferring it to the sensitive optics or the atomic clock. Engineers design the mounting points with shock absorbers made from shape memory alloys that can flex and return to their original form, dissipating energy without permanent deformation. Once the rocket reaches space, the probe faces its first true test of survival, the transition from the warm, protected environment of the fairing to the cold vacuum of orbit. The temperature drops by hundreds of degrees in seconds, and the materials that were perfectly stable on the ground suddenly contract, creating stresses that can crack insulation or misalign precision components. The electronics are still warm from the launch, but they must cool down slowly to avoid thermal shock. Active heaters kick in, keeping the core at a controlled temperature while the outer skin reaches equilibrium. Then comes the first major deployment. The probe's large structures, the antenna dish, the solar sail if one is carried, and the radiator panels were folded tightly for the cramped ride inside the rocket. Now they must unfurl with flawless precision. A sail that is kilometers wide cannot be unfolded like an umbrella. It is packed in layers, pleated like a fan, and held together by release mechanisms that are triggered by electrical signals or by burning a small wire. The slightest jam, a single fold that sticks, and the entire structure could tear itself apart under its own tension. The deployment sequence is choreographed with the same care as a ballet, each step verified by sensors before the next begins. Cameras mounted on the probe watch the unfolding, sending images back to Earth so engineers can confirm that every square meter of the sail is intact and tensioned to the correct value. The same process happens for the antenna. A mesh of gold-plated molybdenum wire, thinner than a human hair, must be stretched across a frame that is many meters in diameter. The mesh is held in place by carbon fiber ribs that pivot outward like the skeleton of an umbrella. If a rib snags or a wire breaks, the antenna's reflective surface loses its perfect shape, and the already faint signal home becomes even weaker. After deployment comes the commissioning phase, a period of weeks or months during which every system is checked, calibrated, and configured for the long journey. The star trackers take their first images of the sky and compare them to their onboard catalog. The magnetometer is turned on, and its baseline reading is compared to Earth's magnetic field, which fades as the probe moves away. The thrusters are fired in short test pulses to verify that their valves open and close correctly. The atomic clocks are synchronized with ground stations, and the error-correcting software begins its first scrub of the memory banks. This is the last time the probe will be under close watch. Once it passes a certain distance, the communication delay will stretch to many minutes, then hours, then days. The engineers on Earth will have to trust that the machine they built can handle the rest on its own. That trust is built on the flawless execution of this initial deployment and commissioning. Every successful step here reduces the risk of a silent failure decades later, and when the final check is done, the probe fires its thrusters one last time to set its course toward the outer edge of the solar system. The launch and commissioning are over. The real mission has begun, but the probe does not simply drift. It must navigate the early cruise phase, passing through the asteroid belt and the realm of the giant planets, where the gravity of Jupiter can either slingshot it forward or tear the whole mission apart if the trajectory is not precisely managed. The long-term planning that began on Earth now becomes the probe's own responsibility, a set of instructions that will guide it through the first few decades, but with the growing awareness that the distance will soon make any course correction a matter of decades, not days. The probe is on its own now, and the centuries of survival ahead depend on everything that has just gone right. Even a perfectly launched probe drifts off course over centuries. The trajectory that leaves Earth orbit is never exactly right. There are always tiny uncertainties in the gravity of the asteroid belt, the slight tug of Jupiter, the faint push of sunlight against the probe's hull. Even the minute gravitational pull of passing comets or the collective mass of the Oort cloud can bend the path by millimeters per second. Those millimeters add up. After 100 years, they become kilometers. After 300 years, they become the difference between arriving at a target star and missing it by millions of kilometers. The probe must correct its own trajectory, and it must do so without wasting a single gram of propellant that could have been spent on science. The first challenge is knowing exactly how far off course the probe has drifted. The pulsar navigation system provides that answer, but only periodically. Between fixes, the computer must rely on its own models of the gravitational environment, models that themselves contain small errors. So the probe runs what is essentially a continuous prediction and update loop. It calculates where it should be based on its last known position and velocity, then compares that to the actual position measured by pulsar timing. The difference is the drift. The computer then plans a correction, a tiny burn from one of its thrusters, to nudge the probe back onto the golden path. But the fuel budget for these corrections is agonizingly tight. Every kilogram of propellant that the probe launches with is a kilogram that could have been a scientific instrument or a thicker radiation shield. Engineers calculate the total delta V, the total change in velocity that the probe will need for its entire mission. That includes station-keeping corrections, arrival adjustments, and any emergency maneuvers. For a spacecraft that must last centuries, the delta V budget is typically a few hundred meters per second. That sounds tiny compared to the tens of kilometers per second needed for the main interstellar boost, but it is enough to fine-tune the trajectory across the entire journey. To stretch that budget, the probe relies on electric propulsion. Instead of burning chemical fuel in a short, intense burst, electric thrusters use electricity to ionize a gas like xenon, and then accelerate the ions out the back at very high speed. The thrust is minuscule, barely enough to push a piece of paper across a table, but it is extremely efficient. The same amount of propellant yields many times the total impulse of a chemical rocket. Electric thrusters can fire for weeks or months at a time, applying a steady, gentle push that accumulates into a precise velocity change. And because the probe has a steady power supply from its generator or reactor, it can run these thrusters whenever there is spare electricity, even while sleeping. Some concepts take this one step further with a solar sail. A thin, reflective sheet, kilometers across, can catch the faint pressure of sunlight itself. Even in interstellar space, the light from distant stars is enough to produce a tiny force. Over decades, that force can be used to make course corrections without consuming any propellant at all. The sail can be angled to steer, adding a gentle tug in one direction or another. The trade-off is that the sail is large, fragile, and takes time to deploy. But for a mission where every gram of propellant is precious, a sail offers a way to adjust trajectory for free, as long as the engineering challenges of deployment and control are solved. The maneuver schedule itself must be planned far in advance. Before launch, engineers simulate the entire 300-year trajectory, accounting for every known gravitational influence, every expected radiation pressure, every tiny nudge. They produce a sequence of maneuvers, each with a precise date, direction, and duration. That sequence is stored in the probe's memory. As the journey progresses, the onboard computer checks its actual position against the expected path. If the drift is within acceptable limits, it executes the next maneuver on schedule. If the drift is larger than expected, it can adjust the timing or magnitude of the upcoming burns within the limits of the fuel budget. But the probe cannot simply fire its thrusters whenever it wants. Every burn consumes power and propellant, and every burn creates a small disturbance in the orientation that must be corrected by the reaction wheels. So the computer must schedule burns during periods when the probe is not making sensitive observations or transmitting data. It balances the need for trajectory precision against the need to use power efficiently and to protect the integrity of the science mission. There is also a psychological dimension to this planning. Earth will watch the probe's trajectory for the first few decades, sending occasional updates to refine the maneuver schedule. But as the light travel time grows, those updates become less frequent and less useful. Eventually, the probe must rely entirely on its own calculations. That moment marks a transition. The probe stops being a machine guided from Earth and becomes a true autonomous traveler, navigating the cosmos by its own knowledge. All of these choices, the fuel budget, the thruster type, the sail design, the scheduling software, are driven by a single question: can we afford the mass? Every kilogram of propellant, every square meter of sail, every watt of power for electric thrusters adds to the cost of the mission. And interstellar probes are already the most expensive machines humanity has ever built. The economic reality is that the trajectory maintenance system must be just good enough to get the probe to its target, but not a gram heavier than necessary. That balance between ambition and budget is the invisible hand that shapes every decision in the design. And it is that same economic pressure that forces engineers to be so clever with every drop of fuel, every photon of sunlight, every second of time. No spacecraft has taught us more about long-duration survival than Voyager. Of course, Voyager 1 and Voyager 2 were designed for a very different job. They were meant to fly past Jupiter and Saturn, maybe Uranus and Neptune, and send back data for a few years. Nobody in the 1970s expected them to still be whispering home nearly 50 years later. Yet they keep going, and in doing so they have become the closest thing we have to a proof of concept for interstellar endurance. What they have taught us is invaluable, but it also reveals how far we still have to go. The most obvious lesson is the relentless decay of power. Both probes carry radioisotope thermoelectric generators that convert heat from decaying plutonium into electricity. When they launched, each generator produced around 470 watts. Today, combined output has fallen below half that. The Voyager team has had to make excruciating choices. They turn off heaters, shut down science instruments, and carefully manage every tenth of a watt just to keep the core systems alive. For a centuries-long mission, that kind of gradual power loss would be catastrophic because the probe would become useless long before it reached its destination. Instrument failures have also piled up. Over the decades, the ultraviolet spectrometers on both probes have degraded or stopped working altogether. The plasma wave instrument on Voyager 2 developed a persistent hum that drowns out real signals. Engineers had to invent software workarounds to filter out the noise. Redundancy has been the hero in many cases. When a primary receiver failed on Voyager 2, the backup receiver saved the mission. But those backups were designed for years of use, not centuries. Some are already showing signs of age, and there is no third copy waiting. The contrast with a true interstellar probe is stark. A Voyager-style design would fail long before crossing the heliopause. Even the radiation environment at the edge of the solar system has damaged components more than expected. Voyager 1 suffered a mysterious glitch in its attitude control system in recent years, a reminder that electronics degrade in ways that are hard to predict. For a centuries-long mission, the power system must either use a different fuel cycle or rely on a fission reactor that can be throttled. radiation hardening must be far more aggressive, and error correction must run continuously rather than being applied as a patch. The biggest difference is autonomy. Voyager still depends on regular commands from Earth. When the signal takes more than a day to travel each way, the spacecraft can wait. But for an interstellar probe, the round-trip time will stretch to years. It must make its own decisions. It must diagnose its own failures, reconfigure its own systems, and choose which data to transmit without asking permission. Voyager proves that survival is possible beyond the heliosphere. It has shown us that a human-made object can pass through the termination shock, cross the heliopause, and enter the genuine interstellar medium. That is a monumental achievement, but 40 years is not 300 years. The margins that worked for Voyager would be stretched to nothing on a mission that must last for centuries. What Voyager gives us is not a blueprint, but a foundation of hard-earned knowledge. It tells us where the weak points are, which components fail first, and how clever engineering can buy more time. Now we must take those lessons and build a machine that can not only reach interstellar space, but live there for generations. A fusion reactor small enough to fit inside a spacecraft would rewrite every rule of interstellar survival. Instead of depending on a steady decay of radioactive fuel that slowly fades over decades, such a reactor could generate power by fusing atoms of deuterium or helium-3, releasing energy comparable to the heart of a star. A single tank of fuel the size of a small suitcase could provide electricity for centuries with no gradual power loss, no need for thinning margins. The same reactor could also drive high-power electric thrusters continuously, allowing the probe to accelerate slowly but steadily over decades, reaching speeds that chemical propulsion could never match. Fusion power is not science fiction. Experimental reactors on Earth have already achieved net energy gain, and compact designs using magnetic confinement or inertial confinement are moving from laboratories toward practical prototypes. For a probe that will launch decades from now, fusion could be the difference between limping to a destination and racing toward it. Quantum sensors represent another leap. Using the strange behavior of particles at the smallest scales, these devices can measure magnetic fields, gravitational gradients, and particle properties with a sensitivity that dwarfs anything we use today. A quantum magnetometer could detect the faint magnetic field of an exoplanet from across a solar system, revealing whether it has a protective magnetosphere like Earth. A quantum gravimeter could map the internal structure of an asteroid or a moon during a high-speed flyby, reading the density changes deep beneath the surface. These sensors rely on atoms trapped in laser beams or on superconducting circuits that operate near absolute zero. Shielding them from the radiation and heat of the probe is a challenge, but the rewards are enormous. A single sensor could replace a suite of conventional instruments, saving mass and power while returning richer data. Self-healing materials could transform the way the probe resists damage. Imagine a hull that contains microscopic capsules filled with a liquid polymer. When a micrometeoroid punches a tiny hole, the capsules rupture and the polymer flows into the crack, then hardens to seal the breach. Such materials already exist in laboratories. They can restore most of the original strength after a puncture, and they can be tuned to react to different types of damage, from thermal stress to radiation-induced microcracks. On an interstellar probe, a self-healing outer shell could keep the pressure vessel intact and the insulation effective for centuries, even after thousands of impacts. The same principle can be applied to wiring, to structural joints, and to the seals around scientific instruments. A probe that can heal itself does not need as many spares. Advanced artificial intelligence will tie all these technologies together. The AI of the future will not just follow pre-programmed rules. It will learn, adapt, and invent new strategies when the unexpected happens. It could redesign its own power management schedule after a reactor anomaly. It could rewrite its navigation algorithms to compensate for a failed sensor. It could even decide to repurpose a damaged instrument, using its flawed readings in creative ways to extract information that a healthy instrument would miss. This kind of AI relies on neural networks and deep learning, systems that can be trained on Earth and then continue learning in flight. The challenge is making sure the learning does not lead to unpredictable behavior. Researchers are working on methods to bound the AI's creativity, to keep it within safe limits while still allowing it to solve problems no human foresaw. None of these technologies are ready for a launch tomorrow. Fusion reactors are still too large and too fragile. Quantum sensors require cooling and shielding that add mass. Self-healing materials have only been tested in short-term experiments. Advanced AI is powerful but still prone to surprising mistakes. Yet the probe that will cross interstellar space is not launching tomorrow. It will launch decades from now, perhaps half a century into the future. That time horizon gives researchers a clear target: develop these technologies to flight readiness, test them in space on smaller missions, and then integrate them into the final design. The path from laboratory to launchpad is long, but every step brings the dream closer. The question is how we test systems that must operate for centuries without maintenance. On Earth, a century of wear can be simulated in months using accelerated aging chambers that bombard components with radiation, cycle them between extreme temperatures, and vibrate them continuously. We can also fly prototypes on shorter missions, like a deep space probe that spends 20 years in the Kuiper belt, to see how they hold up under real conditions. The data from those tests feed back into the designs, refining them until they are ready for the true test, a journey measured not in years but in the lifetimes of many human beings. Every breakthrough, from fusion to quantum to self-healing, will be verified here on this planet before it ever leaves Earth for the stars. That verification begins not in space, but inside high-tech laboratories where engineers try to pack a century of punishment into a few years. They build chambers that simulate the worst conditions the probe will ever face, then subject every component, every circuit, every structural joint to doses of radiation, extreme temperatures, and relentless vibration that would destroy an ordinary machine in days. The goal is to break things on purpose, to find the weak points before the probe ever leaves Earth. Accelerated aging is the engineer's secret weapon. By cranking up the radiation flux far beyond what the probe will encounter in interstellar space, they can compress decades of cumulative damage into a few weeks. A chip that would normally take 80 years to accumulate a lethal dose of ionizing radiation shows its failure mode after just a few months of intense bombardment. The same approach works for thermal cycling. Instead of the slow, seasonal shifts the probe will experience while drifting through the void, the lab cycles the hardware between extreme cold and extreme heat hundreds of times a day, each cycle mimicking a year's worth of expansion and contraction. After a few thousand cycles, any hidden crack or weak solder joint reveals itself. Vibration testing adds another layer. The probe will endure the brutal shaking of launch, but over centuries, micrometeoroid impacts and thruster firings will create a constant low-level jitter that can fatigue materials. In the lab, massive shaker tables rattle the components at frequencies and amplitudes that simulate a lifetime of these tiny shocks in a matter of hours. Sensors watch every resonance, every micro-crack as it forms, giving engineers a clear picture of where the design needs reinforcement. But there is a catch. No accelerated test can perfectly replicate the slow, cumulative effects of time itself. Radiation damage depends on dose rate, and a dose that is delivered too quickly can cause different chemical changes than the same total dose spread over centuries. Thermal cycling at extreme rates can introduce stresses that would never appear with the gentle, gradual temperature shifts of deep space. engineers must carefully calibrate the acceleration factors, validating them against real-world data from older missions. They compare lab results with the actual degradation seen on Voyager and other long-duration probes, tweaking their models until the match is close enough. Still, ground testing can never fully replace the ultimate test of decades of real operations. That is why some mission concepts propose launching multiple prototypes. Instead of building one single, irreplaceable interstellar probe, engineers would send several simpler versions on shorter trajectories, perhaps to the outer reaches of the solar system. These prototypes would operate for 20, 30, or even 50 years, gathering real-world data on how their systems age in the actual space environment. That data feeds back into the final design, allowing engineers to correct flaws that no ground test could reveal. The cost is high, but the payoff is a level of confidence that no amount of laboratory simulation can match. Each prototype becomes a living lesson, a teacher that whispers back to Earth about the subtle failures that only time and distance can reveal. In the end, rigorous testing is the only bridge between a hopeful design and a machine that can truly be trusted for centuries. The probe will be poked, shaken, cooked, frozen, and bombarded until everything that can break has broken, and everything that survives is deemed worthy of the stars. Only then can the builders say with confidence that the machine they are about to send into the void has earned its place among the constellations. The price tag for a machine that must survive 300 years is measured not in millions, but in tens of billions of dollars. No single nation can bear that weight alone. Even the most ambitious spacefaring countries would find the budget overwhelming. The only realistic path is international collaboration, a coalition of space agencies, research institutes, and private partners pooling resources and expertise. But cooperation at that scale is its own kind of engineering challenge. Different nations have different priorities, different safety standards, different political cycles that can shift support overnight. An interstellar probe is a project that will outlast the governments that approve its funding. The political will to start such a mission must be sustained across decades, through economic downturns, leadership changes, and competing scientific priorities. That is a harder problem than any materials challenge. The trade-off between redundancy, mass, and performance drives every design decision. Every spare kilogram of shielding or backup component costs precious payload capacity. Every additional layer of protection reduces the mass available for scientific instruments. The probe that carries 3 computer cores instead of 2 is heavier and more expensive, but it is far more likely to still be operational 3 centuries later. Engineers must weigh each gram against its contribution to survival. The margin for error is vanishingly thin. A single miscalculation could leave the probe with too little power to call home or too little fuel to stay on course. The entire design is a series of compromises, each one negotiated between the desire for maximum scientific return and the absolute necessity of endurance. What justifies such an enormous investment? The answer lies in what the probe could discover. A flyby of an alien star system would transform our understanding of planetary formation, atmospheric chemistry, and the potential for life beyond our sun. Even a glimpse of the Oort cloud, the vast shell of comets that marks the boundary of our sun's influence, would reveal the raw materials from which our solar system was born. The scientific return from a single interstellar mission would eclipse every probe we have ever launched combined. But none of that return matters if the probe fails before it arrives. The survival of the machine is not a secondary concern. It is the entire point. Every dollar spent on redundancy, on shielding, on self-healing materials is an investment in the moment when the probe finally slows down, turns its instruments toward an unknown world, and sends back the first image of a star that humans have only ever seen as a faint point of light. That moment will be the culmination of lifetimes of work, of billions of dollars, and of the political will that made it all possible. And when that image arrives, it will not be a single frame. It will be the first chapter of a story that our descendants will read for generations to come. Every system on that probe must earn its place in a legacy that spans centuries. None of them works alone. The power source, whether it is a radioisotope generator or a fission reactor, provides the steady heartbeat that keeps the computers awake and the instruments alive. The shielding, both passive layers of polyethylene and active magnetic fields, forms an invisible armor that deflects the constant rain of cosmic particles. The autonomy, the artificial intelligence that watches every voltage and every temperature, makes split-second decisions that no human could ever telegraph across light years. The communication system, the laser and its precisely aimed telescope, turns a whisper of photons into a thread that connects the probe to its distant home. And the redundancy, the triple voting processors and the gracefully degrading subsystems, ensures that when one component falters, another takes over without missing a beat. Each of these technologies faces a challenge that seems almost insurmountable on its own, but taken together, they weave a net strong enough to catch a machine crossing the abyss. The radiation that would destroy an ordinary computer is met by hardened chips and error-correcting code. The cold that would freeze a standard battery is countered by heat pipes and smart insulation. The micrometeoroids that would puncture a simple hull are caught by layers of sacrificial bumpers that vaporize on impact. The long silence between commands from Earth is filled by an intelligence that can diagnose its own failures and plan its own future. Every problem has a path forward, not through magic, but through engineering that respects the laws of physics and pushes the boundaries of what we can build. The path from where we stand today to a probe that will leave our solar system for good is long and expensive, but it is visible. Each breakthrough in fusion reactors, in quantum sensors, in self-healing materials brings that moment closer. Each test flown on a shorter mission validates a piece of the puzzle. Each nation that joins the effort adds resources and expertise that no single country could provide alone. The question is not whether we can build such a machine, it is whether we will choose to start. The first interstellar probe will not be built in a single year or by a single team. It will be the work of generations, a project that outlives its founders and is completed by their descendants. But every great journey begins with a decision to take the first step. Watching the development of deep space technology, following the progress of new materials and autonomous systems, is a way to be part of that decision. The mission that finally crosses the threshold between our solar system and the stars is not a fantasy. It is a future waiting to be built, and every mind that turns toward it brings it one step closer to reality. The stars have been silent for billions of years. It is time to send them a message that we are listening.